Well, next topic is, you understand we're trying to develop what you would call a solution of the homogeneous equation. Okay, well then that's what we're going to look into. Right, okay, so if we have a set of k solution vectors to the homogeneous system x prime, vector x prime equals matrix A times x, on an interval I, and the only solution of the equation c1 x1 plus c2 x2 blah 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 plus ck xk is equal to the zero vector is if all the ci's are 0. Then the set of vectors x1, x2, blah, 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 up to xk are linearly independent. And it might be even more important to say, well, what does it mean if they're linearly dependent? Well, if you have that set of vectors and their solution vectors to this homogeneous system on an interval I, and if there's more than one solution, all the ci's equal to 0, of that same equation, c1 x1 plus c2 x2 plus dot 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 plus ck xk, if there's more than one solution, in other words, one of these vectors may be some linear combination of the others, then they're called linearly dependent.
Unbelievable!
Yeah, what the thing about it is, and the thing that you're going to really appreciate, is that there's a nice test. Other than, I mean, trying to see if you can solve this equation for some CI not all 0, that might be a bit of a challenge.
What?
Yeah, a bit of a challenge, but that doesn't mean we can't do it. But there's an easy way to do that, because if you want to test for linearly independent solutions, you know, we have a bunch of solutions that look like this. They're vectors, right? If that's n solution vectors for the homogeneous system x, vector x prime equals matrix A times vector x on an open interval I, we can check that they are linearly independent because the set of solution vectors is independent if and only if the Wronskian determinant, and sometimes you could use this notation for that, but you take all the x's in each one, make them columns of a matrix, find the determinant of that matrix, and if that determinant is not 0, then the vectors, solution vectors, are linearly independent. So, very similar to what we did with the Wronskians of functions, although we don't have to take any derivatives for this one, we can just use the big stack of vector solutions as the columns of the vector. So, here's an example. Show that this vector and this vector are linearly independent over a set of real numbers, and all we do is verify that the Wronskian of, with this vector in column 1, this vector in column 2, as you see here, verify that this determinant is not 0. So the determinant would be e to the negative 3t times e to the negative 2t, that's e to the negative t. Oh, sorry, that's e to the positive 2t, but that's e to the negative t. And negative 4 e to the negative 3t times e to the 2t, I guess, but that would have a, since it's minus a negative, would wind up being plus 4 times e to the negative t. So we wind up with 5 e to the negative t, and of course e to the negative t is never 0. So therefore those two vectors are linearly independent, and that actually helps us to see that indeed the vector c1 times this one plus the vector c2 times this one is the general solution of the homogeneous system, or sometimes we call that the complementary solution.